Okay, so let's take the solenoid, something like this. Okay, and then just like Gaussian surface, right? We have to come up with the Amperian loop. So magnetic field goes like this, right? So what we are assuming is, so the Amperian loop, right, is taken this way, in a rectangular shape. So if I have north and south, right, okay, so one more thing here is, see, we are going to assume, right, okay, before that I have to explain you one more concept. So in a solenoid, what happens is, capitalism, so if I take a solenoid like this, right, so at one point it is going in and another point it is coming out. So another way of showing this is, it's something like here it is going in, the current is going in through this wires, and the other point is coming out. So this would be shown as like this. Do you folks follow what this means? So when you have a loop like this, so at one point it is going in this way, another point is coming out like this. Okay, so the 3D can be shown something like this. Okay, so this is into, this is out, into the paper, out of the paper. So suppose if I take the same thing, right, so you can draw this and you can also draw this. So what happens here is, this is the Amperian loop, just like the Gaussian surface. So we are interested in finding the magnetic field over here. So magnetic field, we already said it's something like this, right? It's going in this direction. So the Amperian loop is where the dl stands, right? Remember, there's a major difference between the Biot-Savart law and Amperian law. So in the Biot-Savart law, the dl will go along with the I. Okay, so if you go back to your notes, you will see that if the Biot-Savart law goes like this, right? If the current is going like this, you would take this as dl. Here, even though we are using the same letter dl, right? It's not along the current, it is along the loop. Okay, so here we say that this point is far away from this, so we assume that the magnetic field here is 0 or negligible. Okay, so since when I have a solenoid like this, right, obviously I am going to have more magnetic field around this area, not here. So if I take a loop up to this point, I can say this point is going to be 0, right, or negligible. Okay, so we are assuming this as 0. And then the magnetic field at this point is going this way, right? So capitalism. So this is your magnetic field direction. This is along the dl, right? So I'm going to call this as A, B, C, D. So A, B, C, D is the Amperian loop. Okay. Anybody having any issues why I have drawn this like this? Current is going in and then coming out, right? That's all, very simple. So this is magnetic field B here because it's going like this, right? But then this is the dl. What can you say about this angle? 90 degree, right? So B dot dl means dot product, which is cos theta. Cos 90 is 0, right? The same thing happens here. So this part becomes 0. So look at this, magnetic field is this way. So this is B, this is dl. So this is also 0. So what we are going to say here is, along this part it is 0, along this part it is 0, along this part it is 0. So we are going to consider only this one. Okay, which means, what it means is, most of the time inside a solenoid, right, we are not very much interested in the magnetic field which is outside. We are more interested in the magnetic field which is inside. Okay, that's why we put a iron core here, and I can use it in different applications. For example, look at this. Any idea what this is? Motor? No, it's not a motor. What does it do, sir? Just wait a second, sir. So again, I have to show it so that everyone can see it properly, right? So if I had something like this, 6 volt. So when you are doing these experiments, right? If this and this are touching, the experiment is not going to work. Why? It's a short circuit, right? The plus and minus, instead of going through this, it's directly going to flow through this, right? Which means it's not going to work as expected. So you have to make sure that these things are not touching each other. Okay. It's actually working differently. It's not supposed to work like that. Drilling machine. It's not supposed to work like this. It's supposed to work differently. Okay, something is going wrong here. When I switch it on, right, it should just go in, and when I switch it off, it should come out. So it will be connected to some kind of a valve, right? So this is called, these kind of valves will be called as solenoid valves, because it is working based on the solenoid principle. Okay, so inside you have got a solenoid, and this is iron core inside this. So you can see this is iron core. So when it becomes, when you flow the current, right, it becomes magnetized, which means it will be pulling inside, right? And when you stop the current, the spring will, can you see the spring here? So there is a spring here, so it will push it out. That's all. So it's something like a on-off valve, right? Only thing, since it is working based on solenoid, it can be called as solenoid valve. Okay. So very often in industries, when you want to flow, switch on and off some valves, right? Water flow valve or yak flow valves, you'll be using this very often. Okay. So pneumatic valves or liquid flow valves. Okay. So all these things will be using this one. It's not supposed to, vibrate like this. It's supposed to just, I don't know why it's doing that. Earlier I thought it was because of the short circuit. So, or maybe the voltage which I am giving is high or low. 6 volt, if I give 6 volt. I'm not sure why it's doing that. Okay. It used to just stop at one point. Okay, the purpose of showing that is solenoid valves have got a lot of applications, okay, in industry. Okay. That's what I said. It's used to, switch on and off of some valves and all, right? Air valves, liquid valves, right? Fluid flow valves, right? So once you make it into electrical circuit, right, you can automatically control it, right? Manually, you don't have to go and close it and open it every time, right? You can say, okay, when the pressure is this much, make a logic circuit and using your computer programming, right? You can say, okay, flow the current through this one, which means when the current is flowing, it will close the valve or open the valve as required, right? So that's the advantage. Anything which is made into electrical, right, you can integrate it with some embedded systems, right, which means whatever you are studying in your computer science, right, you can make use of it and you can control the entire circuit. Okay, so let's come back to the theory here. So I said at this point, since it is far away, right? So even though I'm not able to show it properly in the diagram, it means this is far away. So we are assuming that this is negligible. This and this are 0 because it is 90 degree. So B dot dl is 90 degrees, which is cos 90 is 0. So these two are gone, which means I am worried only about this one. So I am interested in finding the magnetic field inside the solenoid. Okay. So that being said, I'm going to take this distance as x. So if I want the magnetic field inside this, I'm going to say integral of B dot, maybe I'll write it here so that everyone can see it. Integral of B dot dl is equal to mu naught I enclosed. That's my Ampere circuital law. So if I want to add all these things, the way I should write this is integral of A to B, right? B dot dl plus integral of B to C, B dot dl plus integral of B dot dl C to D plus integral of D to A is equal to mu naught I enclosed. But I said these three things are gone, which means I can cancel out all these things, but still you have to write the steps. So A to B, B to C, C to D are gone out, so it can be cancelled. B to C is 0 because it is negligible. A to B and B to C, sorry, D to C, C to D. We said B dot dl is equal to 0 because B is perpendicular to dl. So write down that. Okay. So this is the reason why this is 0, this is the reason why this is 0. Same thing here. So what I am left with is only the last term. So if I do this B dot dl D to A, so D to A. So I am going to assume that the magnetic field in this entire length is going to be same, which means this entire length is going to be same, which means it's constant. So I can take it out. So mu I enclosed. So B comes out. Integral of dl. So if I integrate all this small dl, right? So let's say I have a small dl here, small dl here. So if I add all this dl, what will be the total length? It will be, I'm assuming it to be x. So if I add all these things, it's going to be x. So integral of dl mu naught I enclosed. Everyone following this? Any issues? Integral of dl is nothing but x. So b dot x. Again, right now I am focused on the magnitude, so I can take out the vectors dx. Mu naught is a constant, so just leave it. Okay, so I enclosed means, look at this. So I have a lot of coils going like this, right? So I have a lot of coils here, right? So I have taken the Amperian loop such that I am including only this one. If I had one I here and if I had 10 I's, then it will be 10 into I. So suppose if I said the number of turns is capital N, right? This entire this thing, right? So what can you say about the current? I enclosed will be N into I. So everyone following that? N into I. If I had 1 amp flowing here, if I had 10 turns, it will be 10 into 1, right? If I had 2 amps, 10 into 2. So total number of turns. So capital N is always total number. I like Nevada formula and all, right? Very often we use small n. What is that small n there? Number of electrons per unit volume, right? So there you would have written small n is equal to capital N divided by 3, right? But unfortunately we don't have enough letters, so we have to keep using the same letters. So here the n means total number of turns, okay? So there it is total number of electrons, here it is total number of turns. And then we are going to define small n as total number of turns divided by length, okay? So I can say this is nothing but number of turns per unit length. There we said number of electrons per unit volume. Here we are saying number of turns per unit length. Let me check if I should use L or X. Okay, so I have used X here because that length which I am taking is only X. Right? So carefully listen here. So suppose if I had 10 turns here and if this is 5 centimeters, so the small n will be 10 divided by 5. More accurately 5 divided by 100 because meters, right? So similarly number of turns is given as, number of turns per unit length is given as capital N by X. So now I want to replace capital N in terms of small n. So this comes here, so it will be mu naught n into xi dx. So xx cancels, so I get b is equal to mu naught ni. So that's the final formula which we are supposed to arrive at. Okay. Very easy if you understand the concepts. The only thing you have to practice. Okay, what is the physical meaning of this? As you increase the number of turns, magnetic field will also increase. Okay, in this particular x distance, right? Instead of 10 turns, if I put 100 turns, right? I'm going to increase the magnetic field. That's why you can see why the solenoids are looking so thick, right? So even though the wire is very, very small, they will put more and more turns, which means if you are flowing 1 amp, instead of 10 times, you will be flowing it 1000 times. So the magnetic field will be very, very strong. Okay, but of course it is proportional to I also, right? Does that make sense? So always try to make some kind of a note here saying that okay, B is proportional to N and I. Okay, only then you will understand the physical meaning.